Hi everyone, this is the group setting. Today we'll be introduced to you the password authenticated key exchange, the PAKE protocol. First, we'll be looking at some introduction material and a detailed example and some further directions. So what is PAKE exactly? Let's say a motivation example first. Here on the left is a traditional Diffie-Hellman protocol. It's very nice. It's create a new session key each time, and it provides forward secrecy. If we choose a new private key, A and B each time, but we know that it's very vulnerable to the man-in-the-middle attack. That's because it does not provide authentication. The ifs can easily impersonate the other party by actively engaging with the legitimate parties. So how do we solve this problem? The answer is we need authentication. The idea is relatively simple, but it took scientists over 40 years trying to tackle with this problem. Let's first look at some basic authentication factors. Of course, you can use biological features such as fingerprint and one's retina, but for cryptographic approach, we're going to look at the first two factors. We can use a public and private key pairs to do the authentication. Typically, when we communicate over a public network, for example, HTTPS, there will be a public key infrastructure, PKI. It provides support for the authentication process. But what if we want to have a secure communication channel between two devices on a local network, as in the example on the top right corner? When you want to cast your phone on a TV. Here, we don't have the public key infrastructure. That's why we need the PAKE protocol. So intuitively, the big picture is we want to derive the new session key or temporary key from a common secret shared between two parties for the authentication purpose. In this case, it's a password. So that's why PAKE is called password authenticated key exchange. So how does it work? We derive and exchange our keys based on pre-known common password that held by both the parties. That's also an assumption for PAKE. It's trying to achieve mutual authentication between the two parties. In particular, it's trying to derive a shared secret key of a communication session without revealing the actual password to the eavesdropper, in contrast to Diffie-Hellman, which is a public key pair used here. So that's the basic idea behind it. And we also need a mechanism to verify the two parties are indeed share the exact same password without revealing it. This can be achieved by using, for example, a zero-knowledge proof. So why do we want to use it? First, of course, it's easier for laymen to remember password rather than manage long, tedious cryptographic keys. Second, with some implementation of PAKE, the server only stores the data that is derived from the password, so we even don't need to bother with transmitting and storing the hashed and salty password over the network. Even when the server is compromised, the password can still be safe. We'll say more of this coming later. The PAKE protocol is an umbrella term. There are, of course, many family members that use this idea. We'll only introduce two most common and most used categories, the balanced PAKE and the augmented PAKE. You can see from the timeline over here, it has a quite long history of development for almost 30 years. Here I listed some well-known implementation of these two types of PAKE. We won't go into details for the sake of time. The difference between these two types of PAKE is very easy to understand. Previously, we have only seen Alice and Bob. Now we consider the two parties as Alice and Sola. The balanced PAKE is also called symmetric PAKE, where both parties know the exact password or equivalent. For example, when a user wants to pair two physical devices together, a phone and a TV. A recent Wi-Fi protocol, WAP3, uses a balanced PAKE called Dragonfly. In the augmented, also called asymmetric PAKE, the server doesn't know the exact password, but the verifier derived from it. The server does not have enough info to authenticate the client on its own without the client's input. It's considered more safe than the balanced PAKE, as the password is not stored on the server. So when the server is compromised, it's add additional layer of protection. In all this internet, where data breach happens sometimes, and client doesn't want to trust the server, the augmented PAKE is preferred. Here's another taxonomy of PAKE. It's based on how you establish the secure key for a session. We won't go into detail here as well. Okay, let's look at some crucial property that the PAKE protocol offers. There are also the minimal security requirement for all PAKE protocol to be satisfied. First, the man-in-the-middle attack, of course, because of the mutual authentication between the two parties. The offline dictionary attack is a major security feature that is always mentioned together with PAKE. So if an attacker eavesdrops all the communication and key exchange process between the two parties, they still shouldn't be able to figure out the password by checking against a pre-computed dictionary. This can be easily achieved with the augmented PAKE, because the password never leaves the client, really, while some version of balanced PAKE has trouble deal with this issue. The reflection attack is simply saying the attacker shouldn't be able to impersonate the party by reflecting the message to himself. The forward secrecy is talking about if a long-term secret is compromised, the past session keys that are derived from it should remain secure. To achieve this, we need to derive a proper session key for each communications. Now the non-session security add another layer on top of forward secrecy. It requires if one session has been compromised, it won't affect any other sessions. This can be done by incorporating some sort of randomness into every sessions. For example, you can use a nonce or using ephemeral keys. Okay, now let's dive into a particular example, a well-known and well-established version of the PAKE protocol, the JPEG.
In order to provide protection for the client's password, we'd like to introduce JPEG. JPEG stands for Password Authenticated Key Exchange by Jungling. It is a unique protocol that enables two communicating entities to securely establish a shared secret using a known shared password. JPEG involves two stages. One is one-time key establishment stage. In this phase, both parties exchange messages through the protocol to establish a session key. And another one is key confirmation stage. It is used to ensure that both parties have the same session key. JPEG can be used to resist man-in-the-middle attack. And zero-knowledge proofs is used in JPEG to ensure both parties can trust each other. In the real world, JPEG usually applies in the secure remote password authentication and IoT devices. The JPEG protocol typically operates in two rounds to establish a shared key. In round 1, we have group G with the generator G, shared secret S, and the ZKPs. First, Alice selects two random values and their corresponding ZKPs to Bob, and Bob will also send two random values and ZKPs to Alice. And in the second round, it focuses on securely computing a shared keying material using the exchanged data. After receiving the public values from each other, Alice and Bob compute a shared keying material. This computation involves their own private values and the received values. Then Alice and Bob can derive a common session key from this key material. In JPEG, parties can authenticate their knowledge of a shared password using ZKPs without revealing the actual password. This mechanism reduces the risks associated with exposing sensitive credentials, ensuring trust is established in a secure manner. Even if an attacker is listening on the entire JPEG protocol execution, ZKP ensures that they will not be able to get the password or any related information.
As my group mates just introduced and presented, we have fully showed our understanding of PAKE, focus on security properties, and our preparation for the final comparative analysis of learning JPEG. So what else we need to accomplish? After the research on balanced PAKE, we must continue on other protocols, especially in augmented PAKE. And our plan is to introduce SRP and opaque, since they have the relationship that opaque is treated as an optimized form of SRP, which eliminates most of drawbacks. So it should be much better for comparison. As a recap of our report focus, we're trying to deliver a comparative analysis. It could be compared between Diffie-Hellman and PAKE protocols. We can also compare between balanced and augmented PAKE with our examples of JPEG and SRP, or we can compare between outdated and recent protocols like SRP and opaque. But one thing we need to make sure is that security properties must be considered. To come up with some open problems, our plan is to combine real-world applications, since we have only presented concept of each protocol. So let's think about web authentication and VPN connection that we used to access to the canvas, also the Wi-Fi access, the Apple iCloud services. They're all related to PAKE protocol. Also, we need to figure out their security issues. For example, users often reuse their password across multiple platforms. So how this situation impacts on PAKE-enabled system. That could be one open problem. Seems like we still have a lot to do, to learn, to write. And it will definitely take our understanding of PAKE even further. And here are our references. And thanks for your listening. Let's go for the Q&A section.